Alright, so this is Physics Lecture 1. We're going to start by talking about force and acceleration and mass and a little bit about the implications of those. So besides just writing down a formula, force equals mass times acceleration, we're going to talk a bit more about conceptually what that means. So not so much just can you plug in mass or acceleration and find force, or have force and find mass or acceleration, but more about what those things really mean. So anyway, let's start with the equation, just so that we can look at it and talk about it. So first of all, let's talk about what a force is. A force is basically any influence or any influence that can cause a mass to accelerate. And that makes sense looking at the formula, because a force equals any mass that is accelerating. So we could say that if something has no mass, it has no force, or if it has no acceleration, then it has no force. And that's obvious from the equation. You could figure that out mathematically. But think about what that means for a minute. That means if you have a mass just sitting there, it doesn't matter if it is the Earth, the mass, at least the size of the Earth, or a shoe, or anything else around you, if it's not moving, then it has no acceleration. So keep that in mind for a second. If there's no acceleration, then there's no force. Okay, so let's talk about units for a second, just so we can kind of understand what the force is really saying and how that came to be. So mass, in SI units, is measured in kilograms, and acceleration is meters per second squared. And we'll get into acceleration a little bit more in a second, talk about why that is. So then the unit for force is in Newton. Actually, I'll write that down. Newton, usually just abbreviated with an N. And, as you can imagine, that is actually kilograms times meters per second squared. And so that is basically what it looks like. It's some kind of mass that has kilograms, some kind of mass that's measured in kilograms. That's going some kind of distance over time squared, and we'll talk about that, like I said, in a minute. Okay, so let's talk a little bit about what that means. So then, let's say I have a mass that is accelerating, or let's say we have a mass, let's draw a box here, and there's some force coming this way. Let's say this is a net force. So a net force means that although there's other forces acting on this box, all those forces added up, meaning, even if you have this on the ground here, let's say that's actually touching, you have a normal force going up, and you have force of gravity going down, and whatever other forces, air pressure, it's all around it. Doesn't matter, we're just saying the net force, which means all those forces added together, what's left over. And that's this vector here. So that means that we have some kind of force that's pushing this, we'll call it this box to the right, so it has a net force. So what that means is, we know it has mass, right? And we'll even say it's 1 kilogram. So it has mass because it exists, it's there. And so from this, if we know that vector force, and we know the mass, and we can find its acceleration just by solving for it in the equation. But understand what that means. The fact that we have this net force means that we have an acceleration. So if you have a mass, and it has a force on it, a net force, then it has to have an acceleration. That also means that if there is no net force, there is no acceleration. Now, it may sound pretty simple at first, and I think anyone can just kind of intuit that, but that can be a little more difficult when you're talking about a problem or any other kind of conceptual thing. So, for example, let's say that I have, let's use a different color just to shake things up a little bit. Let's say I have a car here. I'm not going to draw a super good car. Not that I could if I wanted to, but I'm not even going to put too much effort into it here. Okay, so let's say we have a car. Okay, and this car is traveling, let's say west, and I really don't care how fast. Let's just make an arbitrary number. Let's say 50 meters per second. So its velocity is 50 meters per second to the west. Okay, and that's a constant velocity. It's not changing, just 50 meters per second. So what does that mean about the net force on it? Does it have a force? So let's look at that equation again. It obviously has a force. It obviously has, let's take that back. It obviously has a mass. It doesn't matter what that mass is. So it's moving. It's moving at 50 meters per second, which, it's moving. It's going at a decent pace here. So what does that mean? Does it have a force acting on it? Does it have a net force? Well, it definitely has forces on it, obviously. but it has no force, it has no net force. And the way you know that is because it's not accelerating. Acceleration means that acceleration is basically a change in velocity over time, but it is going at a constant velocity, 50 meters per second to the right. So if it's going at a constant velocity, it can't have an acceleration. And what that means is it has no net force. So that's where things get a little bit tricky. And problems can be made pretty difficult with that. They can be made to sound really difficult to solve. They can make just everything sound really difficult, and the problem just seems like it's going to take 100 years to do all the calculations for. And in reality, it's almost, I don't want to say a trick question, but it's testing your knowledge of that. They could say that you have some object or some mass, and it's going across a frictionless table. It's called a box again. And they can say that it's pushed or whatever, and it doesn't really matter. It's on a frictionless table, and it's moving to the right at 10 meters per second. And they could say it comes off the end of the table and it falls off. And its acceleration falling down is 10 meters per second squared. And whatever, and they could say all these things, and they could say, while the box is on the table, so when it's right here, moving, what is the net force acting on this box, or what is the acceleration on this box? And the answer is there is none. There is no acceleration on the box. It's moving at a constant velocity. Anytime you hear constant velocity, it means there is no acceleration. That asks you what the net force is. What's the force on the box? And there is none. If there's a force, because mass is an intrinsic property, it can't. Well, we're going to say in this system it can't change. So that means that if your acceleration, if you have some kind of number here, you have to have some kind of number here. If this goes up, if your mass stays the same, which in most instances that's the case, when mass stays the same, when force goes up, acceleration has to go up. If net force goes down, the acceleration has to go down. Just keep that in mind. So that's a little bit on force and what that can mean. So anyway, what you got to understand with that then is how do you make something accelerate faster and faster? If you say you have some kind of net force, so once again, let's use a box again. So we have a net force on it. So we have this force vector here. Is it accelerating faster and faster, or is it not? So if you're on a graph here and you have the movement of this box, and let's say that this is its let's say time here, and this is velocity, and we'll say it's meters per second as the units on that, and this is just seconds. Okay, so we have a net force. So what does this graph look like? And let's keep in mind that velocity is basically change in displacement over time. So you have this force, and it's a constant force. Let's say you have a force of 10, constant force, net force of 10 newtons. So what is that graph going to look like? How's it going to move? How is the velocity going to increase over time? Well, you have a constant force, which means you have a constant acceleration. If that force doesn't change, then that acceleration can't change either. Just like we said, if you up the force, the acceleration has to go up. But acceleration, keep in mind, is like I wrote before, it's a rate of change of velocity over time. So the rate of change, not the change in velocity over time necessarily, but the rate of change and how that's moving. So when you have a constant force like that, that means basically that with 10 newtons, your graph's going to look something like this. As time goes up, velocity gets faster and faster and faster, but it's at equal units. It doesn't go any faster. It doesn't increase any more from 5 to 6 seconds than it does from 1 to 2 seconds. It's a constant acceleration. So what does that mean about having let's say a non-constant acceleration? Well, that graph, let's say this is velocity and that's time, that graph is going to, let's say you have force is increasing, so you're going to have something more like this. Now what that means is you don't have a constant force anymore. So this force on this box, this force here, this vector, it's maybe 10 newtons here, but then 3 seconds later it's now, let's say this force is now 15 newtons, and then later you have 20 newtons, and just keep in mind that means that maybe there's someone there pushing the box, and they're pushing harder and harder and harder, whatever that may be, at a constant rate or whatever, and it's hard to tell if it's constant or not necessarily just from looking at a graph without actually plotting down numbers and things like that, and I don't think we really need to do that right now. It's not super important. It's just for the conceptual understanding of it. But the point is it's no longer going to be going to be a straight line because it's going to be going a lot faster because of this equation as the force goes up, not it goes up, doesn't matter the increments it goes up in, but the fact of the matter is the acceleration is going to change. So as the acceleration changes constantly, let's say it changes constantly, like in this situation, it's going up 5 every time, the force going up 5 every time, you're going to have a non-linear graph like that. And that's because it's going to have a faster rate of change from second 5 to 6 than it will between seconds 2 and 3. As shown here, it's getting a lot more of an increase in velocity from here than it was here. Okay, so what does that mean that the acceleration graph looks like? Okay, so let's say we have this one again. Okay, so velocity and time there. So that's a constant velocity. You're increasing, not constant velocity. It's a constant acceleration. Your velocity is increasing linearly, right? So the acceleration graph is going to look something like this. Not just an arbitrary spot, but the point is you have some kind of positive acceleration, but it's constant. So keep in mind that this still means you have an acceleration just because this line is flat. Doesn't mean there is zero acceleration. If it was at 0, if you had a line here straight on the x-axis, well then you have 0 acceleration. But let's just say this is a 5, arbitrary number there. That's 5 right there. So you do have an acceleration. You have a number there, and so that makes this linear straight line. But what if I had something more like this? Okay, now I have a linear graph here, so acceleration is changing at a constant rate over time. So acceleration is increasing, but let's say every second it increases by 5 meters per second squared. So you have, at 1 second you're at 5, and then at 2 seconds you're at 10, and then 3 seconds you're at 15. It's increasing linearly. But now what does this do to the velocity graph? So let's look at that. This is where it can get a little bit tricky if you don't have some kind of units, or not units, but numbers to actually calculate things and actually see if it's changing constantly or not. With just graphs like I drew here without really numbers, you can't really tell, but you can still kind of tell if you have two to compare to which one has a constant increased acceleration or not. So on the constant acceleration, so referring to this graph with acceleration, the velocity we said might look something like this, okay? But with this one, the velocity versus time graph is going to be a little bit different. It's going to be a little bit even faster because let's just go. So that's not linear, but we're going to say that's faster. So we can tell between the two of these which one is increasing faster over time. So let's say you go this much faster here between seconds 5 and 6 on this graph. But on this one, let's say between seconds 5 and 6, it's a lot more vertical. You have a lot more of an increase in velocity from seconds 5 to 6 than you did on the other one. And so that one would refer more to this graph, and this one would refer more to that graph. So like I said, without actually being able to plot out points or seeing points to be able to put into an equation to find out if it's constant or not, I doubt anything they could really ask you a question saying, oh, here's which one is this constant or not. But you can tell, like I said, you can tell by looking at it, looking at a graph, like looking at acceleration versus time graph, if its velocity is increasing constantly or not. And once again, this would mean a constant acceleration, but it has an acceleration. Would mean that the velocity is increasing, but the velocity is increasing constantly. And if you have this one here, this means that the velocity is no longer increasing constantly. And so there you go from that. You can kind of tell what's going on with velocity. So hopefully that helps a little bit on understanding exactly what force and acceleration is, and how that affects things like velocity. And yeah, I hope you enjoyed that, and I will be back with physics. We'll call it lecture 2 another day. Thanks.